Thank you all for joining us today. My name is Rogelio Sullivan. I'm the project manager here at PowerAmerica. And on behalf of the PowerAmerica team, I'd like to welcome you all to this regular technical webinar series. Normally, these webinars occur on the first Wednesday of every month, but today we have a special guest speaker from the Clean Energy Manufacturing Analysis Center at the National Renewable Energy Lab of the Department of Energy. So the U.S. Department of Energy's Clean Energy Manufacturing Analysis Center provides objective analysis and up-to-date data on global supply chains and manufacturing of clean energy technologies. To do this, CEMAC develops innovative models, data, tools, high-impact publications, and harnesses the first-rate talent of the Department of Energy's National Laboratory Network in partnership with industry, universities, and research affiliates. And today's topic is particularly germane to PowerAmerica and the activities that we're involved with in helping to promote silicon carbide power electronic technology. So without any further delay, I'd like to introduce Ms. Samantha Reese, who's our speaker today. Samantha is at the National Renewable Energy Laboratory, and she and her colleagues, Kelsey Horowitz and Tim Remo, did the analysis that resulted in this report, which is available and which she'll present today. So Samantha, the floor is yours.
All right. Well, thank you so much for that introduction. And also, thanks for introducing my colleagues, Kelsey and Tim, are here with me today, and Maggie Mann, who's Technical Director of CEMAC, is also joining us online. For today's presentation, we're going to quickly run over a little bit more about CEMAC, although that was a pretty good overview of what it is, look at what this project entailed, and then really get into the meat of the project, which is the global supply chain analysis, of the bottoms-up cost modeling, and then the bottoms-up cost modeling, and that allows us to do some scenario analysis, and we'll run over a few of those scenarios, and then a quick wrap-up. But before we get started, we really want to thank the Department of Energy's Advanced Manufacturing Office for supporting this project. All right, so what is CEMAC? As you said, CEMAC is a virtual center created by the Department of Energy and headed by NREL in collaboration with other national labs and university partners. The objective is to do objective supply chain analysis to inform research and investment in the development of clean energy technologies. Clean energy technologies is a broadly defined term that includes anything from technology that produces clean energy to technology that allows you to use less energy. So part of the CEMAC analysis encompasses everything from doing capacity production of various regional manufacturing countries and understanding what part of value chain each country is playing, to doing bottoms-up cost modeling. And I don't know. There we go. Sorry, I was trying to make my cursor go over these. So bottoms-up cost modeling that highlights regional cost differences to help with manufacturing location decisions. We look at trade flow maps, which in conjunction with the bottoms-up cost modeling can tell you where the value add along the supply chain of a final product is. And then we also look at market projections. We do not do the market projections. We utilize market projections to understand if there is any material or other constraints that would keep a technology from being widely adopted in the future. The end result of the analysis is looking at the global supply chain. It helps tell you where, again, the raw material is, where the production and capacity is by location. The bottoms-up cost analysis helps understand what is the driver of the manufacturing costs in different regions, whether it be labor, capital, taxes, et cetera. The piece of the location and scenario analysis, it can help really highlight what a specific region offers in terms of manufacturing. For instance, if you have an energy-intensive manufacturing process and your grid is only up 25% of the time, that is not going to be a good location for that particular manufacturing. It also helps tell you what the influence of quality, currency, other pieces are. And then finally, the big takeaway that people can get from a techno-economic analysis that CEMAC does is it provides a rigorous method to compare pathways. And so a lot of different technologies, solar being a good example, tie this into their roadmaps because it's a way of identifying and prioritizing R&D areas based on cost and the technology impact. So for our project this year, our key takeaways is that wide bandgap and specifically silicon carbide adoption is growing. The U.S. has a dominant position in wafer and device manufacturing. Power module manufacturing, where you integrate the devices into the power module, is done globally. However, it is more concentrated in the Asian regions. And medium voltage drive manufacturing tends to concentrate closer to the customer base. From doing the bottoms-up cost modeling, what we found is that the material costs are very much dominating. For the silicon carbide wafers, over 40% of the total cost is in materials. When you look at the devices, the diodes, the MOSFETs, over 50% of the cost is materials. And then when you get into the power module, which was an IGBT-styled module, over 60% of the total cost is material. Finally, we were able to run multiple scenarios showing paths to ultimate lower costs throughout the value chain. So our silicon carbide project for this last year. Silicon carbide, why are we looking at it? Well, it's really the wide bandgap material of choice. It allows you to operate at higher temperature. It has a higher operating voltage, which is key because for the product, we're looking at medium voltage variable frequency drives, and medium voltage is defined between 1,000 to 10,000 volts. And then it has higher switching frequency. Also, as an added bonus, silicon carbide is more mature than gallium nitride, and we also have U.S. manufacturing already for it. So why wide bandgap material in variable frequency drives? Basically, if you look at a functional diagram of a variable frequency drive, the wide bandgap diodes and transistors can be substituted in to have a big increase in efficiency, and when coupled with the being developed electric motors that work at higher frequencies, it allows for a smaller footprint. Also, you get a higher voltage and power operation. The motivation behind looking at silicon carbide and wide bandgap devices in the medium voltage drives at this time is that it's really an opportunity for growth right now, and we need to understand the drivers of regional manufacturing costs and plant location decisions, and we're wanting to inform the research investment in the development of the wide bandgap technologies. For the project, we specifically focused on ingots through variable frequency drives. We did not look at the processing of the raw silicon carbide material. And so we were looking at 3.3 kV devices, since those are kind of the cutting edge technology right now. And the reason we were focusing on medium voltage industrial variable frequency drives is industrial energy use is the highest, is the largest consumer of electricity, and the Department of Energy feels that if variable frequency drives were used in place of motor systems, and so you eliminated all the constricting valves and such, you could get a significant energy savings in that arena. The other thing we were doing for ours is when we were looking at specifically the power modules and the variable frequency drives, we were looking at very near-term designs. We were not looking at designs that are more advanced that will utilize some of the silicon carbide wide bandgap capabilities as much as they potentially could. So global supply chains. We specifically were able to get information for wafers, epitaxy, and chips of who is producing and what the capacity is in those locations. As the graph shows, the U.S. is a dominant wafer supplier, and for devices, it's basically divided 1/3, 1/3, 1/3 between the United States, Europe, and Asia. Japan is only working on 6-inch wafers, but in the U.S., we have both 4- and 6-inch. Again, U.S. is one of the top 3 countries, particularly strong in the wafer fabrication. One of the reasons for this is we're very good at delivering top quality wafers, which is something that from our industry interviews we were told is particularly important. Dow Corning, due to being a multinational large firm with established U.S. manufacturing, and Wolfspeed Cree both help put us in this position. Wolfspeed is benefiting from being vertically integrated, and they actually use silicon carbide for their production of their LEDs, so they had a particular amount of experience in this area. For devices, we found that the trend is towards large multinational power electronics players, people like ROM, Infineon, and the industry through acquisitions and consolidation is moving towards being vertically integrated globally. One thing that was a takeaway is the limited number of silicon carbide suppliers is hindering the ability to multi-source, and people are reluctant to adopt the technology unless they can have multi-source for their components. In looking at power modules doesn't have any technology for manufacturing that allows really you to track the capacity of production in a country. And so instead of being able to explicitly call out which countries are dominating in power module manufacturing, we instead concentrated on looking at where are power modules capable of being manufactured of vertically integrated companies. So this map does not show any contract manufacturing. And based on interviews, it seems that power module manufacturing is often, the companies will outsource it to contract manufacturers. This is just showing that for vertically integrated companies, where they have facilities that we believe are capable of manufacturing an IGBT-sized module. Again, the primary concentration is in the Southeast Asia and China area. As I described, one of the things that CEMAC does is look at the material in a component to understand if there is anything that will limit its widespread adoption. And so for power modules, we found that basically there are no rare materials that would hinder it from being widely scaled. Base plate and the circuit board are copper and aluminum, the wire bonds are aluminum, the housing is plastic, and so all readily available materials. We found that, as I was just describing, that the module manufacturing falls within 2 categories. Companies that are vertically integrated, so they have facilities in-house. We found that in companies that are highly customizing their modules for their end use, they're more likely to do the module manufacturing in-house. And then again, contract manufacturers in Asia, and this is primarily used when you have a set design and you're in high volume. Again, for medium voltage VFD manufacturing, there is not the ability to assess what the capacity is of any given facility for manufacturing the drive. Especially what we found was most of these drives, the main piece for the manufacturing is assembly, so you need a giant warehouse, and so you are only limited by the size of your facility. What we're representing on the map is some of the top companies from market reports that manufacture medium voltage drives. And from our interviews, we know that they tend to manufacture the drive close to their end customer. And so these are large multinational companies, so their manufacturing plants are throughout the globe. Again, with the variable frequency drives, there are no critical materials being used. Now, I want to take a step back and say that at this time, it is our understanding that there is no company actually providing silicon carbide medium voltage variable frequency drives to the market. And so, but basically using the current drives, we know that what would be a limiting factor was the availability of the silicon carbide modules. We also know from our interviews that the transformers tend to be custom manufactured, and so they're going to also drive the overall cost in the drive. While drives are not a high volume market, only 12,000 units were sold in 2015. It is a high value market, and it was about $2.7 billion. So those 12,000 units represented a $2.7 billion market in 2015. China is the most rapid growing consumer of variable frequency drives, although there are significant sales in America and EMEA. As I mentioned before, the key insight is the drives are typically manufactured closer to the end customer. It reduces your lead time and it allows rapid response to customer needs. Okay, the meat of our analysis, the bottoms-up cost modeling. So our manufacturing cost model base case is we're modeling the effects of core country factors, things such as labor, electricity, corporate tax rates. In this early stage industry, especially for upstream components, the competitiveness is less driven by core country factors, although over time this could change. For all of the models, we made similar assumptions for the countries, that they have the same cost of debt and equity, the same production volumes, yields, and wafer diameter. Again, we understand, like, for instance, Japan is just doing 6-inch wafers, where in the U.S. you have both 4 and 6-inch. But for the base case model, we're just making the same assumptions to have an apples-to-apples comparison. We're assuming no subsidies. Again, we understand that certain countries will highly subsidize equipment to help grow an industry. We're assuming the same knowledge and capabilities of all the firms. We know that there is dominance in the United States with having, again, Cree, Dow Corning. We're assigning the same risk associated with firms regardless of the country of manufacturing. And for the wafer model, for the base case, we're assuming 100% capacity utilization. In our regional cost models, we determine the minimum sustainable price, the MSP, that a company is going to need to sell in order for it to pay back the capital and operating expenses during the lifetime of the plant. So for the silicon carbide wafers, with an epi layer on top, we're assuming that you are manufacturing 5,000 6-inch wafers a month. And again, we are doing it for 3.3 kV devices. And so for our regional cost modeling, we found that the difference for a wafer are largely attributed to labor costs. So even though this is highly automated, the labor is influencing the regional cost difference. And then also cost differences in overheads, things such as SG&A, R&D, and taxes. The key overall drivers are materials, the high cost of high-purity silicon carbide powders for bowl growth, and the high cost of consumables, the diamond wire, the diamond slurry, the polishing of silicon carbide, which is so hard, is a significant player in what the overall material costs are. The lower yields and the longer time for the throughput is also driving the wafer cost. We do believe that the overhead costs will decrease as the industry scales and matures. So for the silicon carbide chips, we know that there are a number of different devices. However, for the purpose of our analysis and because it made sense for the variable frequency drives, we're looking at the diode and the die MOSFET. Typically, silicon MOSFETs do not perform as well at these voltages and powers, and so they have to use silicon IGBTs, so that's how we decided on what devices to model. Again, they're at 3.3 kV. In the case of the devices, we found that the labor had little impact on the overall cost. Basically, the wafer price was constituting the vast majority of the cost, since this is a highly automated process, followed by equipment and facilities. So for a silicon carbide MOSFET, assuming an 8 millimeter squared area, the chip MSP per chip cost is $1.92. Now, for a silicon carbide diode, which is going to be about 3x bigger than the MOSFET, again, you're going to have a slightly lower overall processing cost, but because the amount of chips that you can get per wafer is less, since they are 3 times bigger, and the wafer cost dominates, then we found that the MSP for a diode is $561. All right, silicon carbide modules. For the silicon carbide module, we were using a 1.7 kV design that's in existence today, and using a modified version of that, we assume that you have a capacity of 1 million per year. We found that really it's a highly automated process. Labor has very little impact on the overall cost. At a volume of 1 million a year, your equipment and facility costs are also going to be very small. And there's really no specialized equipment you're going to need in the near term, so you can leverage existing packaging facilities and contract manufacturers. And in our current scenario, we think that the silicon carbide diodes and MOSFETs are about 46% of the cost. Now, it should be noted that for this model, we basically did that if the U.S. made chips, we inputted the U.S. chip cost into the model. We understand that, chips are very easy to source globally, and that this would not necessarily be what someone would do. But for the purpose of our model, we use the price of the local chips to input. And overall, we determined that silicon carbide IGBT-styled module with 3.3 kV devices was going to be between $279 to $291 a unit. For our variable frequency drives, we were modeling a 1 megawatt drive. We determined a 1 megawatt drive based on discussion with Department of Energy and PowerAmerica of what made most sense. We determined it would take about 45 3.3 kV power modules in the drive. And the drive cost, as we discussed at the beginning of the presentation, is significantly influenced by your overall material costs, followed by labor. There is no specialized equipment necessary to assemble a drive, but it is, based on our interviews, very time-consuming. So we were assuming it would take about 8 weeks of construction with 3 laborers with 40 hours per week. And so between the material costs, which is over 70% here, and labor costs, which is about 17%, that's the vast majority of the cost in a variable frequency drive. And the overall drive is $170,000 to $200,000 a unit. Again, one of the big takeaways for the variable frequency drive manufacturing is the manufacturers want to locate it close to the end user because they're wanting to provide the support and integration without requiring the end user to need to go through intermediaries. Compared to if you were to try to use a silicon-based medium voltage drive, one of the big differences is you're going to have fewer modules that you need. You get to reduce your cooling. By reducing your cooling and needing fewer modules, you right away reduce the overall footprint of the drive. Long term, as they have better product development and more adoption, you're going to need even fewer power modules, which is going to further reduce your cooling needs. It is possible for the silicon carbide power modules to eliminate the transformer, and since the transformer was a significant piece of the drive cost, that is an exciting opportunity, and that would then even further reduce the footprint of the drive. There, however, remains a number of barriers to adoption of the silicon carbide wide-bandgap products. As exciting as they are, most of the industry is looking to integrate silicon carbide are very conservative, whether it be automotive or motor drives, and so they're really wanting to see additional in-situ, like reliability testing to prove out that there is not going to be any long-term problems. Further, the high substrate costs and lower yields is driving the cost higher. Integrating into the systems, in certain cases, you can kind of drop in silicon carbide in place of silicon. However, in most cases, if you really want to utilize the capabilities of a wide bandgap device, you need to turn your entire product, and product cycles tend to be 3 to 10 years. And so people are just now starting to look at redesigning to use the full capabilities. As I mentioned earlier, there are some supply chain issues. Again, they want to have as many multi-source capabilities as possible, and right now there's a limit to the number of places that you can get silicon carbide wafers, silicon carbide devices, or power modules. And there's just an overall lack of customer knowledge. PowerAmerica, though, is doing a great job of kind of educating the next generation workforce to help overcome some of this. In regards specifically to silicon carbide-based VFDs, this is a very conservative marketplace. Reliability and downtime are very important. And so our interviews basically highlighted that, at least initially, they're really going to focus on the improved reliability and not even highlight to customers as much that silicon carbide or wide bandgap devices are enabling it. And the overall cost for a variable frequency drive is a further hindrance to the market adoption, even though there is some analysis that shows that you can get a fairly rapid payback, especially if you're depending on valves or other constrictions in your system with the implementation. The just upfront cost is hindering people from moving in that direction. So from our bottoms-up modeling and our interviews, we found that across the entire value chain, quality is critical. That's really what people are looking for. We found that with wafers and chips, the manufacturing yield is highly influencing what the cost is, and that you are going to be more successful with more processing know-how that you know. Existing access to the capital or existing facilities will facilitate rapid adoption and help drive like manufacturing location decisions. Specifically on the devices and the wafers, access to existing silicon manufacturing facilities reduces your need for CapEx upfront and enables you to realize economies of scale, even though the current market is pretty small. As I described, one of the great things the bottoms-up cost analysis allows us to do is to do some scenario analysis, both of what the existing marketplace looks like and futures. So here we have a more realistic representation of what we think the difference between China and the U.S. is. And so with China, we think that probably you decrease the production volume 80%, where you're only processing 1,000 wafers, which decreases your plant capacity utilization to 40%. You increase your yield loss because we've heard that the U.S. has the highest quality and the highest yields. And however, when you offset that by subsidizing the equipment and facilities at 50%, you basically come out about at par with what the U.S. is likely when you decrease our plant capacity utilization to 80%. However, the U.S. firms are leading in production of 150 millimeter wafers, which are lower cost per unit area than 100 millimeter wafers, so that does give an overall advantage. When you start to look at future scenarios, though, of how can we further reduce overall costs, this is comparing China scenario to a U.S. scenario with the intention of pursuing pathways for cost reduction. And the U.S., for example, by decreasing your yield loss 10%, decrease your SG&A costs, which we believe happens as you get to a more mature marketplace. Increase your crystal growth. If you do that, and then in China, if you, again, increase your production to 5,000 wafers a year, which increases your plant utilization, decrease your yield losses, decrease your R&D spending, and increase crystal growth, it looks like you could implement either scenario, and the U.S. and China would both have cost reductions and be about on par. One thing to note for chip manufacturing is, in pursuing the Foundry model, you upgrade existing silicon fabs to allow production of silicon carbide as well. The Foundry model has many benefits. It eases your scaling up, it lowers your capital expenditures, and given that the predictions for the silicon carbide device market is rapid growth over the next few years, this is a great direction to go in. However, using a semi-world fab database, the majority of silicon fabs are in Japan, EMEA, and China. And so there is probably a need in the U.S. for equipment growth if we want to maintain a dominant position. Moving on to a power module, a potential scenario for reducing a power module cost would be if you move to a single direct bonded copper. For our base model, we were using multiple ones. If you remove the base plate and then you utilize the wide bandgap capabilities of silicon carbide and you further shrunk the model, you could reduce your power module cost 33%. And that's not taken into account if you had moved upstream and reduced your wafer and your device costs. And so, you know, there's a way of, because in this scenario, the silicon carbide devices are now 69% of the power module cost. And so then if you incorporate your upstream reductions, it's a way of getting silicon carbide power modules on par with silicon. All right, the value of the CEMAC analysis is, you know, we examine the supply chains to identify potential material limitations before you do years of research and figure out that there's only enough krypton on Earth for, you know, a couple devices or some. We identify areas of research based on the cost, so run scenarios so we can figure out what the impact of the advance would be. We can help provide support for proposals and help companies understand the impact of change on the products throughout the value stream. There are a lot of ways you can work with CEMAC. You can reach us at themanufacturingcleanenergy.org and learn more about what CEMAC itself does. And if you're wanting further details of any piece of our analysis, we have an entire report that is now available. It just published, fresh off the presses, and you can access it at this URL, or you can reach out to any of us with questions if we don't have an opportunity to answer something today. All right.
Well, thank you very much, Samantha. That was an excellent presentation, very informative, very broad in your coverage, and obviously very informative for our audience as well. So thank you very much for the analysis that you've done and for sharing that with us today. Because there's so many folks online, I want to open it up for Q&A, but I want to ask folks to please use the chat function at the top of your screen. There should be a drop-down menu saying chat, so if you type in your questions, I'll read them so everyone can hear them clearly, and then Samantha will respond. So are there any questions at this time? Can we get a copy of Samantha's presentation? Yes. Samantha has given me a version that I can share, and I'm sure her contact information is here, so you can email her as well. You can get it directly from Enron.
Yes, again, as I described, the report itself is much more detailed of what assumptions we were using for our bottoms-up cost analysis. It goes into more detail of regional capacity and production. And again, it covers all the assumptions we made and whatnot. So.
Thanks. The second question is on page 7 on the diode versus MOSFET cost comparison. Please explain why the diode cost is higher.
Diode cost is higher because it is 3x larger than the MOSFET.
In actual physical size.
In actual physical size. So the MOSFET is 8 millimeter squared area, and the diode is 25 millimeter square area. And given, therefore, that you're going to get less diodes from your wafer, it drives up the cost, even though your actual processing costs are lower for the diode than the MOSFET.
Yeah, and that's an assumption that we made. So we took that 8 millimeter squared for the MOSFET, assuming a specific on resistance from actually a paper that I think came out of PowerAmerica from a non-Argowal. There's a lot of range in that, and same with the diode. So this was assuming, I think, a 20 amp diode, so that'll depend on the current as well. But the processing costs are lower for the diode, like per wafer.
Thank you. And just for clarification, Anand Agarwal was at the Department of Energy at the time. He was our technology manager. He's since retired. Are there any more questions? I can't seem to mute whoever's making that noise, but if you have a question, please type it into the chat window, or you can just unmute yourself and speak since there are not a lot of people asking. Okay, I guess that means that, Samantha, you were just so comprehensive and covered all the bases that you left no questions unanswered. So I want to thank everyone for joining us today. Thanks to the entire CEMAC team at NREL, and we look forward to seeing you at our future technical webinars.
Thank you. Thank you for giving us this opportunity to share, and please don't hesitate to reach out if you have questions or there's any further information we can provide.
You're welcome. And as Samantha said, she gave your contact information. If you want the detailed report, please contact her directly, or you can contact me if you have if my email address. I don't want to just send a blast out to everyone, but I can get the report and the presentation to you as well if you'd like. All right, thanks everyone. Have a great day. We'll meet again soon.
Thank you so much.